Class, today it's lesson 41, it's functions. What's our objective? Get ready?
Functions.
Functions. You're going to learn how to write a function based on a rule or relationship. You'll make a table, a graph, and then we're going to decide which relationships are proportionate. And a lot of this you've been doing for 3-4 years, and I know because I taught this in Intermediate 5 this week. So it'll be a little bit of review, but there'll be some new things because we're putting everything together. A function is a mathematical relationship between two sets of numbers. A function's rules apply to the input so that we can generate an output. Here's an example of a function. Ethan is going to shovel driveways, the snow, to earn money this winter. And the rule is, for every driveway he shovels, he earns $10. That's the rule. So I would input one driveway, his output is $10. Input 2 driveways, his output is $20. 3 driveways earns him $30. That would be pretty cool. Now the rule for a function is, for every input, so one driveway, there's only one output, $10. Meaning if he shoveled 2 driveways, he should only get $20. He wouldn't get $20 and $30. That wouldn't make a function. So you have to follow the rule. For one input, there is one output. How many outputs? Get ready? One. A function, you can think of it as a machine. Whatever you put in, then a rule applies. Like this would be 4 times the input, and then you get an output. That happens to be 4 times the side length of a square. Let's look at the side length of an equilateral triangle. So the perimeter of an equilateral triangle is 3 times the length of its side. Write an equation that expresses this relationship. Use P for perimeter, S for side. So I rewrote the sentence so you could see how you can translate English to math. The perimeter is P equals 3 times the side length, S. And we like to use dots, or you can even leave the dot out. So P equals 3S, and then part B says choose 4 different side lengths, make a function table. This is a function table. This is a graph. So just make sure some students are confused, which is a table is a list of ordered pairs. A graph is a location on a coordinate plane. So our easy numbers to pick usually is 1, 2, 3, 4. You can even throw a 0 in there if you want. Show the side lengths and perimeters of equilateral triangles. So this is the side length. This is the perimeter. If I input a side length of 1 foot, for example, my perimeter would be 3 times that, or 3. If I input a side length of 2 feet, my perimeter would be 3 times that, or 6. This would be 3 times 3, or 9. This would be 3 times 4, or 12. These become ordered pairs, and then I can graph these on my graph. 1, 3, it's a relationship. Input 1, output 3. Input 1, output 3. See the ordered pair? 2 and 6, 2 and 6, 3 and 9, 4 and 12. And then I look at my relationship. Does it go up 3 over 1, up 3 over 1, up 3 over 1? Has the same relationship every time. And it's in a straight line. If it's in a straight line, we call it linear. Linear. What is it called when it's a straight line? Get ready?
Linear.
Linear. And if you ever forget, what does linear mean? Take off the er. It's a line. It means it's in a straight line. Okay, let's do another one about Xavier and Yolanda. Xavier and Yolanda have a game going. So Xavier says a number, and Yolanda says a number. She puts a rule to it, and she has an output. Xavier says 2, and she goes 4. And then he says 3, and she goes 5. He says 4, and she says 6. What is Yolanda doing to Xavier's number, Joseph?
She's adding 2.
She's adding 2. So we're going to say that Yolanda's number is Xavier's number plus 2. Yolanda's number is Xavier's number plus 2. Mathematically, we're going to put an equation to that. We're going to say y is Xavier's number plus 2. We always start our equations with the output. So to find the output, I would take the input and add 2. And you check it. Is it this rule every time? Does it work every time? Yeah, it does. That would be the rule, so we know it's right. Let's graph these ordered pairs. 2 and 4, over 2, up 4, over 3, up 5, over 4, up 6, over 5, up 7. And at this point, after you have about 3 or 4, you can say, oh, I see what's going on. It's going on these little diagonal corners here. And I can keep going and going and going and going. And then I check it. Is it a line? Yes, it's linear. And does it happen to go through the point 0, 0? No, that's the origin. So it doesn't go through the origin, but it is a line. We're going to keep exploring with that in the next example. Okay, so we've had 2 examples. We had the triangle one, the perimeter one. We had Yolanda's and Xavier's example. We're going to look at another feature of their tables. Output divided by input. It's a certain ratio and it means something special. We're going to see what that ratio is and compare this output divided by input to this output divided by input, see what we get. Okay, output over input. What's my ratio? Get ready?
Output over input.
Good. In, out. Output divided by input. So it's 3 over 1, 6 over 2. What's my next one? Get ready?
9 over 3.
Good. And the next one, get ready?
12 over 4.
Good. Thank you for paying attention and being with me. Let's reduce. That's 3. Reduce. That's 3. Reduce. That's 3. They're the same every time. If you divide the output divided by the input, and they're the same ratio every time, we call it a proportional relationship. What do we call it? Get ready?
Proportional relationship.
Proportional relationship. There's 2 other features for being proportional. We're going to get to that. Let's check Yolanda's and Xavier's. Output divided by input. Output divided by input. What's the next one? Get ready?
6 over 4.
Next one, get ready?
7 over 5.
Very good. Let's divide those out. That's a 2. That's not a 2. Already I can tell these numbers aren't going to match. That's 1.6 rep of 10, 1.5, 1.4. They're all different. If the numbers do not match each other, if the ratios are different, it's not proportionate. So that's one differentiation. Well, what does proportionate mean? What do we care? Well, there's 3 requirements for proportionate. A proportionate relationship has 3 features, and we've seen them all so far. The first one, linear. What does it have to be to proportionate? Get ready?
Linear.
Linear. The next one is it goes through the origin. The triangle one went through the origin. I think I forgot to plot that point though. The second one didn't. Has to go through the origin. What does it have to go through? Get ready?
Origin.
Origin. And the third one, the ratio has to be constant. The ratio is constant. So those are the 3 requirements to be proportionate. So all 3 have to be true to be proportionate. But if you find one that's not true, that's all you need to disprove. It's not proportionate. So we're going to try this one. I'm going to skip that whole wordy paragraph and go right to the equation, table, and graph. Yes, Preston?
So that one linear problem that we did, it was going to mean that it would go through the origin.
It would have. I just didn't draw that point. If you took my ruler and went like this, it would have gone right through there. It would have. Okay? I just stopped too soon. All right, here we go. This one's the area formula for the area of a square. Side length squared. So if I had a square with side length of 0, is there any area? Yeah, that's a pretty small square. In fact, that square doesn't exist. There's no side length at all. So there's no area. Let me do this. Side length, and this is area. Okay? So this is really my input. This is my output. Before I ever calculated my area, wouldn't I have to know what the side length is first? So the first number I'm putting into my function is the length of the side. Then my output is the area. So that's, I know it's written area, side length, and this says side length area. That's just how it is. It's just, they reverse it because you have to know what the side length is first to calculate the area. Let's pick some easy numbers. I need some help here. If my side length is 1, what's my area? Colin? 1, because why?
Because 1 squared is 1.
1 squared is 1. Rachel, this one. Formula for area is side length squared. My side length is 2.
I don't think it's right.
2 squared, which is 4. Okay, good. Hopefully we're all together. Michelle, what's my next one? 3 squared, which is 9. There it is. Here's some ordered pairs. Let's graph them and see what we get. 0, 0. It's at the origin. Boom. We've met that requirement. 1, 1 over 1 up 1. Okay, it's looking pretty good so far. 2, 4 over 2 up to 4. I'm starting to question. 3 and 9 over 3 up 9. Is it linear? Well, there's that line. There's that line. There's that line. They're all different. And the way we would graph it, it have a little bit of a curve to it because it's going to have to go. And then if we did 4, it'd be up here at 16, right? 4 squared. So it really, I couldn't go up 3 over 1, up 3 over 1. It's going to go up 5 over 1, up 7 over 1. It doesn't have that constant change. So, not linear. Therefore, it's not a proportional relationship. I could stop there. It's not proportionate. If I wanted to do a ratio, output over input, output over input, output over input, output over input. Different or same? They're different. The ratio is not constant. So it's not proportionate. What is it, class? Get ready?
Not proportionate.
Not proportionate. So now you know what it looks like on the table, the graph. We've tested these out. We have one last example, and we'll go super fast. Actually, give me a thumbs up if you feel like I get how to graph it. I get the table. Give me a thumbs down. I'm not sure out on the table part or the graph part. I don't see any thumbs down, so I think I'm going to skip this example. Let's go to our practice set. 283, 284, you got to do problems B and C, and I've got requirements. I'll let you know.